Greetings and welcome to Lab 1, Introduction to Data, Part 2. So in this part, what we're going to do is we're going to take a look at how to get to do a little bit of parsing of our data. So we're going to do a little bit of skills that we need in R, and then we're going to go and apply those skills on the on your own part. And I'm going to help you out with the on your own. So I'm going to do pretty much most of those with you, partially because we're going to cut them out. We're only going to do the first one, the fifth one, and the sixth one. So anyway, more about that in just a bit. Okay, so when we left off in the last one, we were working with how to do mosaic plots and how to do summaries of numerical data versus categorical data. Now we're going to take a look at how to parse out data and get just parts of a data frame that we want to work with. How do we, say we wanted just the males that were older than 30 or something along that line. So the trick for that is using the square brackets. So for example, if I go CDC and I go square brackets and I put in 567 by 6, then what that's going to give me is a single data point. And if you recall, let's go ahead and do names again here real quick. If you recall, the six variable 1, 2, 3, 4, 5. Let's see, 1, 2, 3, 4, 5, 6. There we go, 6. The sixth one was the weight. Okay, so that's the 567th case or participant in the study, and that's their weight. It was 160 pounds. So I was able to go in to the data frame and yank out just a single data point by basically giving it its row and its column. That's a good way of thinking about it. If you think about it in terms of a spreadsheet, I gave it the row number and the column number, and that was how I was able to figure out exactly what that data entry was. Now we can use this to our advantage to help us pull out sets of data. So let's do a little experiment here. Let's put in 1 and then put in a colon and put a 10 in to the R console and see what that gives you back. And notice what that generated for us was the first 10 digits. So for example, if I put 4 colon 8 in there, it'll give me the numbers 4 through 8. And so that's a really handy trick, and it's very similar in other environments like in Excel and in MATLAB and other places where they use this same notation to say, give me a range of numbers with a starting number and an ending number. So what that does for me is that allows me to do the following. I can go in and go CDC, square bracket again, and I can put in 1 colon 10 comma 6. And what's that going to do for me? Well, that's going to give me, excuse me, that's going to give me subjects 1 through 10. That's going to give me their weights. So that's the weights for the first, second, third, fourth, all the way to the 10th person. So I'm able to go in and parse out or grab just, excuse me, just a sec there, sorry about that. I can go out and pull out just the pieces of the data that I'm interested in, okay? Well, what if I'd done the following? What if I'd said CDC, square bracket, 1 colon 10, comma, and left the column blank. Notice I told I want rows 1 through 10, but just left the column blank. And what's that going to do for me? Well, that gives me all of the first 10 variables. In other words, it gives me general health, everybody. It says I didn't want just column for weight. I wanted all of the columns, okay? Contrast that to the following. What if I went CDC, square bracket, comma, and left the first part blank and put in 6? Hang on to your toupees, because we just got, 20,000 of, well, actually it only went up to 10,000, so that's enough already. I'm crying uncle. It showed me on the screen the prints there. So whizzing by was 10,000. I said, you didn't really want to see all these. A little trick here, just so you know, one of the things you can do is you can clean up your console quite quickly by holding down your control key and hitting an L. And that'll clear the console for you, so you get a fresh console. So hold down Control and L, and that'll kill the console for you, which is kind of nice, okay? All right, so that's what we're looking at here is just one variable or just one vector. We can also get that by using the dollar sign. So for example, an equivalent command to doing, let me go back up here for just a minute. So remember this one right here, this gave me the first 10, right? Another way I can do that is I can go CDC, and then I can put in weight, and then I can go square bracket 1 colon 10. In other words, I can tell explicitly which variable I want. I don't have to rely on the column number. Notice I'll get back exactly the same numbers both ways, okay? All right, so a little bit about logic and subsetting now. So hopefully in your algebra experience, you've worked with the less than, the greater than, and the two conjunctions that allow us to connect logical statements, the and the or. We're going to use those also in R to help us parse out data. So for example, if I wanted just CDC gender, and I put in a double equalities, that means equivalence in logical terms. That's important that you use a double whammy equals when you're doing logic. And I put in M. What that would give for me is a whole slew of true and falses. Okay, and what that does is it's true when it's a male and it's false when it's a female. So I mean, it gives you back a grundle of true and falses, and what we know is wherever we see the word true, that was a male, and whenever we see the word false, we know that was a female. Similarly, I could put in CDC $age, and I could say what I want is I want all the ages that are greater than 30 years of age. And again, a whole bunch of slew of true and falses are going to come flying by me, and every place where it's true, it means then they're older than 30. Okay? So now this is really nice because when you put those conditional statements into certain commands in R, when it sees a false, it omits it. When it sees a true, it grabs it. In other words, whereas there's a 1, it says, oh, I want that. And whereas there's a 0, it says, I don't want that. So for example, if I wanted to go and get just the males from the data here, in other words, I just wanted only the males, I could set up a new data frame that has just males in it. So let's call that M data for male data. And I'm going to set that equals to, this is an assignment character. Just a quick aside real quick. You'll notice in the lab they use this, which means that's a left assign. A left assign is just fine. If you want to use a less than with a hash, that's cool, but you're also welcome to use the equals, which you noticed in these labs I've been doing. You'll see in pretty much all code that you read from professional art coders or people who write books, they won't use the equal sign. They'll use the assignment tool, okay? They work exactly the same. To make life easier, we're going to use equalities, okay? All right, so anyway, back to what we're doing here. Make this equal to a subset. There's a very cool command in R called subset. Subset, not subet. Subset, okay? Oh, I can spell really. There we go. Now, subset works very much like set builder notation in algebra. The first thing you need to do is tell it what is the elements of the set. What do these things look like? Well, in our case, the elements of the set are from CDC. So this is where I want you to go to grab the things that I'm making a subset of. And now I put in the condition. And so what is our condition here? Well, our condition is that CDC gender equals male. So I go CDC gender, and then the double whammy equals again, and then anytime it is a categorical variable, it needs to be in quotes. Anytime that it is a numeric variable, it does not get put into quotes. Okay, so if you're using a letter, then you've got to put it in quotes. If you're using a number, you do not put it in quotes. That's the basic idea behind it. Okay, and so when we do that, we notice now over in our data environment over here that we have a new data frame with 9,569 observations with 9 variables. In other words, we have parsed out just the male data. So we do a head M data here. Sorry about that. I seem to have a frog in my throat here. Notice that every one of the gender items are going to be male for this entire data set. Okay, so what if I want to get the males that are, say, older than 30? Okay, so I just want that part of my data set. Well, I could go male and over 30. I'm not going to put underscores like they do in the book, just to make my life a little bit easier. And I'm going to put equals, and I'm going to say subset, again, using the subset command. And, well, let's see. We know how to get males. To do that, we're going to go what? Well, first of all, I got to tell you where I'm coming from, right? I'm coming from the CDC data set. And I go CDC gender equals male. And now I need to use the conjunction and, because I want to have and in here, right? Look, so I put between them, I put the word and, right? So I want an and over here. Well, it turns out that the and is the ampersand, or the general middle symbol. I don't know if you remember what that looks like. It's this guy right here. It's the second function, or the shift above your 7. So if you hit a shift 7, you get the AND command. Okay, so that thing counts as an AND. Well, what was the AND? I wanted them to be over 30, and so I'm going to put here CDC age greater than 30. So again, contrasting this, a categorical variable I need, or a letter, I need to have it in quotations. When it's a number, I just put the number in, okay? And an enter, and look, we've now got yet another data set with 7,244 observations on 9 variables, and so that's the data set where you're male and you're over 30. So I pulled out of the entire 20,000 just the ones that meet those conditions. So it's a very, very handy tool. It's a nice thing to have. I'll take just a quick second here just to go back and review some algebra with you, just to make sure this sort of makes sense from an algebraic standpoint. So if you recall way back in the dark ages of your algebraic experience, that there was this thing called set builder notation. And in set builder notation, it looks something like this. You had a parentheses, you had an X, and then some sort of a colon, and then you had a corresponding condition here, right? So there was some condition to be a member of this set. Well, that's exactly how subset works. So subset really is synonymous with that. In subset, in the case we were just working with, we had to have CDC, right, which was our X. That's the set that we're getting from. That's the colon here is corresponding to the comma. Let me do a little color coding here for you. So this right here, oh, come on, switch colors for me, you silly thing. I want this color. Oh, wait, I'm grabbing the wrong tool. My bad, sorry. Got to pick the right tool for the right job. There we go. Okay, there we go. So this corresponds to this, doesn't it? Okay. And now the condition part right here, well, where's the condition? Well, in our case, we had what? CDC ampersand gender equals, or excuse me, that was a dollar sign, not an ampersand. Gender equals, and we had the double M equals male. Okay, so this is the first one we did for the M data. So the thing to notice here is that, again, this part right here, that's the condition that corresponds to it. So this is very synonymous to set builder notation. It's something hopefully you've had a little bit of experience for in the past, okay? And then just to keep here for just a second, the word and in mathematics has a very specific meaning. Well, that's equivalent to, you'll have to forgive me, I can't draw an ampersand to save my life, but I'm going to do a good try, my best here. There we go, there's my ampersand, okay? That's equal to an ampersand in R, okay? And then the word or in mathematics is equal to the straight bar in R. So the bar, where that resides, that's above your return key. If you look at the shift, it's the // it's the second function on that key, it's the shift on that. That's how you get the word or. And if you need to, maybe go back and remind yourself how the words and or work mathematically, or post something up in discussions, and I'll be happy to give you some references to help you out with that. Okay, so let's go back into RStudio now, and let's go see if we can use some of this newfound knowledge. All right. So what if we wanted to get the lab is, what if you wanted to get men over 30 and with gender equal to male, or excuse me, what do you want? Gender equal to male or 30. So to do that, all you need to do is come back in, hit the up arrow to replay the command, come in here and get rid of the ampersand, and I hope I'm calling that correctly, the ampersand. If I'm wrong, send me a text and let me know. And then put that in, and that's an or, okay? And notice we're going to get a different data set this time. I didn't change the word and, I probably should have, my bad. Not overly worried about that. We'll get more of this as we move forward. This is just an introduction to it, but we will need this material again later on in future labs. So make sure that you understand how subset works. That's a very important command. It's going to be very useful for us in later work. All right, let's switch back into talking about graphical analysis of numeric data. So we've done a little bit of graphical analysis for the categorical data, but now we want to take a look at graphical analysis for numeric data. And the only one we've looked at so far was that scatter plot we did earlier on of height by weight when we had 2 variables. But what about if we wanted to do a graphical analysis for a single variable? Well, let's go back and take a look at height again. So let's take a look at the CDC of the height. And so we'll just start off with do a summary of that. Let's look at the numerical summary of that first before we get to a graphical summary of that. So we'll go summary, CDC, HE, height, okay? And when we do that, we get back the following numbers. We get the minimum, we get Q1, we get the median, we get the mean, we get Q3, and we get the max. Now, if we wanted to plot the information that was given by the 5-number summary, which is basically all of these numbers except for the mean. The mean's not part of the 5-number summary. This guy is actually not included in the 5-number summary. The plot that does that is called a box plot. It basically takes these 5 numbers, plots them on a number line, and then draws a cute figure around them. So let's go ahead and do that. Let's go ahead and generate a box plot. So to make a box plot, it's really quite easy. You just type in box plot, and then you tell it the variable that you want to do it of. So we're going to go CDC, and we're going to go HEIGHT. And boom, you get a box plot, okay? Now a little bit of interpretation of what the box plot says here. Anybody who falls more than 1.5 interquartile ranges above Q3 or below Q1 gets a circle. Those are suspected outliers. They're suspected data points that are different from the rest of the distribution. Anybody who's within the whiskers, we consider those to be the more normal or more, what we expect to occur. The dark black line in here in the middle, that's the median. That's at 67. The maximum here, that's the 93. Notice the 93 is represented on the data set, but it's a suspected outlier. Then we also have a suspected outlier at the min at 48 inches, okay? And so the heights that are not suspected to be outliers all reside within these 2 whiskers, which inside of the whiskers here. So the edges of the boxes are at Q1 and Q3 respectively. These ends of the whiskers here, if you take the distance, if you take 1.5 times the width of the box, in other words, this distance from here to here is the interquartile range. If you take 1.5 times that distance, that's this distance right here. And so you mark a line right there, and that gives you the end of the whisker. Same thing on this distance right here. That's 1.5 times the interquartile range is what that distance is. And anybody who falls beyond that, we change our representation and we start putting them in with circles, indicating that those are suspected outliers. All right. Okay, well that's pretty cool. So we see some interesting information given us. There's a lot of people in the middle, and there's a few people on the outsides with respect to their heights. Okay. Well, another way that we can look at this is using what's referred to as a histogram, okay? And a histogram is a very nice plot. The nice thing about a histogram is what it does for us is it gives us, besides, a nice visual for where the center would be in the variation, it also gives us a shape, and those shapes are going to be important. So let's go ahead and take a look at the histogram of the same data set, of the CDC of heights. I'm going a little out of order from the way the lab does it, but that's okay. Okay, and we end up with the following. We end up with the heights looking something like that. Okay, no, that tells us, and it was kind of in that same thing in the shape. By the way, we can go back and look at the box plot here. Is if we contrast these to each other, they both look like that they're roughly symmetric. But in terms of determining shape, the box plot is not a good tool. Okay, the box plot mirrors interesting behavior that will show up in a histogram. Let's come back over here one more time on the histogram, and I want to change it slightly to what's going on with what I've got in here, and I want to change the number of breaks in here to 50. Okay, so let's go comma and put breaks equals not 50. Let's go 10. Not 50. That would be bad. Let's go breaks equals 10. When we do that, it didn't change it too much, did it? Maybe because that's what it was using. Let's try it. I'm sorry, but I hadn't tried this up front. I'm just thinking off the cuff here, so I want to try something a little bit different and see what it does. Yeah, breaks equals 1. That was a really bad idea. See what it breaks. What it does is it changes the number of bars. Let's go 25. Let's see what that does. There we go. So how many bars you basically have is the way you can think about that number. And so by doing that, we get a little bit more bars, which we start to see that, yeah, it looks like it's roughly a symmetric distribution. A little wee bit skewed to the right, but not very much. So that distribution is roughly symmetric, all right? Okay, more about histograms in a minute. I'm getting a little bit ahead of myself. Let's go back to taking a look at a little more about box plots. And in particular, what we want to do is we want to go ahead and generate a new data set, okay? or excuse me, a new variable to take a box plot of. And the way we want to do that is we want to take a look at two variables that we want to relate to each other. And there's a very handy tool in R that lets us do that. It's basically the tilde, and it tells us that what we can do is we can take a response variable and model it by a predictor. So before I go any further with this, let's go back over to the whiteboard for just a second here, and let's get a fresh whiteboard up. And I want to just remind you a little bit about function notation, because it turns out that this notation we're about to use is very analogous to function notation. So if you recall from function notation, there was this y equals f of x thing. Remember that? It tells us that y is a function of x. Well, the y here is what we refer to in statistics. That's called the response variable. And the response, if you think about that back in algebra, that was the dependent variable. It was the output variable. And so the response, oh, excuse me here, I didn't want to put an equal sign down. That was a mistake. Let me erase that. The response variable, the equal sign in here in R is going to be replaced by a tilde. And it tells me that the response is based upon a predictor. Some sort of a predictor, some sort of something that tells us how that response is generated. So for example, if I think that the height is based upon the gender, in other words, think about it for a second. We know that height, it differs whether you're a man or a woman, doesn't it, right? So I think the height can be better predicted if we know something about the gender. In other words, the gender will do something about predicting the height better for me. So this construct right here in R, we call this a model formula. But the thing to keep in mind is it's new vocabulary, but it's very similar to something you've already looked at, because you've already looked at function notation in earlier work, and it's very similar to that. Okay, there's not a huge amount of difference conceptually wise to what we're doing here. It's you're saying that this is predicted by this. Okay, here's the huge difference that we'll get more into as we get through the course, is we're no longer using equals because it's a predictor. And what we mean by that is that it's not hard and fast. Like here in a function, if I put it a 2, it's always going to give me back out the same number. That's not necessarily true, going to be true in statistics. More about that as we get further into the story. Okay, so back at the ranch here. So why were we interested in this model formula? Because what I would like to do is I'd like to take a look at two box plots and compare them to each other. In particular, I don't want to look at just the heights of everybody. I want to take a look at the heights of the males, and compare that to the heights of the females. So we can do that. We can come in and go box plot. And now what I can do is put in CDC. And I type in heights. And now your tilde, that is above your tab key. If you look above your tab where your tick mark is, that's a shift tick, gives you the tilde, okay? And so now I'm going to put in there the heights, okay? So I'll put in CDC height. Oh, what did I do wrong here? Hang on, I'm gonna pause here for just a second. Oh yeah, that was a duh, wasn't it? I paused just a second so I could look at it and went, oh yeah, I did the height by the height. I want to do the height by the gender, Mike. You guys are probably yelling at me going, no, don't do that. Yes, okay, there we go. So I wanted the height predicted by the gender. There we go. Yes, that's much better. Okay, so now we have a side-by-side comparative box plots. And as we suspected, the heights of the men are going to be distributed differently than the heights of the women, aren't they? And we'll come back after we've generated separate data sets for men and women and show how to do the easy, for now, the easy way to do histograms for each of those individually. Because we're going to generate, and in the on your own, we're going to go ahead and generate data sets for the men and the women independently. Okay? All right, so the next thing that we want to do is we want to go back in and calculate an interesting set of numbers based upon our data set, okay? In particular, what we want to do is we want to go and create the BMI, and I'm trying to remember whether or not I actually have done that or not on the previous lab, and I don't think I did. So let's go ahead and do that real quick. And if I did, oh well, we're going to do it again, all right? So we're going to generate a new variable called BMI, all right? Body mass index. And what body mass index is equal to is it's equal to the weight of an individual divided by their height squared times a fudge factor, okay? So, oh, in fact, I know I didn't do it. I'm in my notes now. I know where I'm at, so I haven't done this yet. Okay, so the BMI, the body mass index, the way you do that is you take your height and divide it by, you take your weight and divide it by your height squared and multiply that by a fudge factor. So that's what we're going to do. So parentheses, and we're going to go in for the entire CDC, and we're going to go for every one of them. We're going to go in and calculate the BMI for everybody who's in there. So we're going to need to know what their weight is. And we're going to divide that by CDC, their height. And what we need to do is we need to go ahead and square that, just the height. So order of operations is understood by R. It knows that it's going to take the weight and divide that by the height squared, and then the fudge factor is 703. More about what that fudge factor is about in the lab if you want to read up about it. But this is going to create a new vector for us called body mass index, okay? So we now take a look and we notice there's a new vector. It's got one row and 20,000 entries within that row. This is a data vector, okay? And in there are all of the BMIs for all 20,000 of the participants, okay? Body mass index is sometimes used as a measurement of health. It's purportedly a much better measurement of your ideal weight than just using weight. If you noticed, one of the earlier scatter plots we did, there is a relationship between your weight and your height. And so BMI supposedly takes that into account, so that, you know, knowing how tall you are, you should weigh more. And so it's a much better indication than just your straight weight. It's kind of a unit number that you can use on any individual. So if your BMI is below 30, then that's supposed to mean that you're, you know, relatively speaking, you're supposed to be in good shape, okay? All right, so let's go ahead and take a look at a box plot of the BMI as compared to what people reported as their general health. So see if there's some sort of a relationship between those two. So we're going to go box plot, and we're going to go BMI. Notice that we don't have to put anything but BMI in because we just made a variable that's BMI. It's a single vector. It's not contained within a data frame. And we want to model that based upon the CDC variable general health. Okay, and so if we make a box plot of those two, notice I'm going to go ahead and do a zoom here so you can see all of the variables. I'll take a second to generate it here. There we go. So notice that this is the body mass index numbers based upon whether they say that they're excellent, very good, good, fair, or poor. And what we see is that what, as people rate their health, in other words, they say their health is excellent up to poor, is that the median body mass index is going up, isn't it? And so, as I said, usually if your body mass index is below 30, that means that's a rough measurement of being somewhat in the healthy band of things, okay? And if you're above that amount, that's not such a good idea. I think 25 is like kind of a threshold, and if you're 30 or above, then they're saying, yeah, you're in trouble. So we've got a fair number of folks that are outliers that are above there and above 30. We've got some people, the body mass index is ridiculous. There could be some misinformation in the data set also. There is always possibility of typos and such not, as we'll talk about in just a minute. Okay, cool. So another good way of looking at things is, of course, is to look at a histogram. A histogram is another incredibly good tool for looking at single variables, all right? So let's take a look at a histogram of the body mass index. So we can go hist, and you can go BMI. And it shows you again what the body mass index looks like. By just looking at this, it looks, although it's kind of hard to see how the tail's coming down here, but it looks like the body mass index for our data set for everybody is skewed to the right. In other words, it's got a tail off to the right. There's a lump of of body mass index is basically between about 15 and 40, and then it tails off really quickly, actually between 15 and 35, and then it starts tailing off over here. So the shape of this distribution looks like it's approximately skewed to the right. Let's take a look at the histogram of the ages of everybody who's present here. Okay, let's do that one. So I'm going to go hist CDC age. Pardon me, got to pause for just a second here. Okay, back, sorry about that. What do we see? Well, we see that there is definitely a skew to the right in this one. It's much easier to see in the ages, and we would kind of suspect that, is that, you know, as you get older, the population starts to tail off, doesn't it? Okay, let's take a look at another histogram here. Let's look at histogram of heights. As we looked at this one earlier, and that one looks like it's approximately bell-shaped. Okay, it looks like it's got kind of a bell shape to it, more or less symmetric when we talk about the heights. Okay. All right, one more time on the breaks command. I want to make sure I go over that one with you one more time. Let's do that with BMI, and let's put breaks equals 50 in there, because that's what they ask us to do in the lab. So we ought to stick to some of the stuff at least that they tell us to do in the lab. And what it does is it breaks it down even finer, and it makes it easier to see, just as it was like with the age histogram, that the BMI is actually skewed to the right. So remember that breaks command. It basically tells you how many bars you're going to do. It's not quite that, but it's very much that. So we'll roll with it, okay? All right, so that's the end of the lab that's done in the console. It's now time to change our focus onto the on your own, and for that we're going to open up an R Markdown file. So we're going to go to the make a new file, go to R Markdown, and we're going to call this assignment 2. Okay, we'll say okay, and voila, we get the boilerplate, and basically from line 8 down we're going to go ahead and just get rid of that, and then we're going to go ahead and save this right away. So click on save. Get the spinning wheel of death on my Mac. There we go. Call this assignment 2. And I'm going to make a new folder. Remember, it's good to keep your stuff parsed out like this, and I'm going to call that assignment 2. Okay. Oh, apparently I've already created this folder, so we'll call it 2A. So I must have done this once already. So we'll create that, and then we'll go ahead and save it. You guys just call it assignment 2. Alrighty then, so now what? Well, now that I've got this built, what I need to do is go in and work on the on your own part of it, okay? So the first thing that we're going to do here is we're going to put in, let me put this up so you guys can see it again. Click on the Markdown Quick Reference underneath that question mark there. Because remember, this is really kind of like your cheat sheet to help you with this word processor. That's what you're doing. You're working in a word processor, and you got to know where to get things. Unlike in Microsoft Word, where you click on things to get stuff, here you type things in. So knowing how to do things in here, this little cheat sheet is going to help you a lot. So we're going to put in a header in here, and we're going to put in, say 4 hashtags, and we're going to put in lab 1 for that header, okay? And then when we finish this, we're going to put in another set of hashtags, and we're going to put textbook exercises, okay? All right, so let's go ahead, and we're going to do the first problem, but we're going to change it slightly. So I'm going to go over to the HTML document where the lab is, and I'm going to go ahead and steal that first sentence and just copy and paste it in. And we're not going to do the weight versus the desired weight. I am almost positive that there is some typos in the desired weight category, and it just messes with the whole lab. The desired weight for somebody who's 180 pounds is reported to be 680 pounds. I don't think they were trying to become a sumo wrestler. I think that must have been a typo. And so we'll save it for another day as to what to do when you get mistakes in a data set, how to get those data points out of there. But for now, I think what we'll do is just go with BMI. The mistakes seem to be just in the desired weights, no place else, okay? So we want to make a scatter plot of weight versus BMI. So that's what we're going to start off with. So we're going to change that since we just created the BMI variable. So now we're going to come down. When you finish your sentence, it's always good to put a double space at the end. That just kind of, trust me, will make life easier. And we're going to insert an R chunk. So come over here to where it says chunks and click on insert chunk. And then come down here. And the first thing that we're going to need to do is go back up to the very beginning of the lab. And we need to go and cut and paste that first source command that we started off with. Copy that thing and paste it in here. That way we know for sure that it's going to work in case later on I'm going to show you how to clear all of this data out of here. And we want our markdown file to still work even if that data is not currently present up in our environment. Okay, so we're going to tell it, hey, go get this and just in case. All right. And so what we want to do after that is go ahead and make ourselves another R chunk. I want to keep these separate from each other. It's always nice to kind of have R chunks that are separate to kind of tell what they're doing. Okay, not required, but just a style thing more than anything else. For me, I find it easier to read if I keep R chunks that are doing separate things separated from each other. Okay, so what do they want us to do? Well, they want us to make a scatter plot of weight versus BMI. Well, that's pretty easy. We're going to go plot, and then we're going to go what? CDC weight by BMI. Because remember, we have the body mass index, seeing it's sitting right there, right? And oops, I better make one more thing. My bad. I need to make sure I define BMI in here also, just in case it's not currently present. So let's go ahead and put that command in here. And actually, it's really easy to do because I can come down here and steal it from the console. I can just copy and paste it right out of the console. It's a very nice feature. So anything that was in the console, you can cut and paste that and put it up into your R markdown file. Okay. All right. So we're going to plot those two. So here's a very cool trick, is that you can actually go up and run a chunk without having to compile the entire document. So if you click on chunks again, and it says run current chunk. So if I run current chunk, I can see whether it's going to work or not. And by Jove, it did. It plotted my BMI by the weight. So the weight's predicting the BMI. And what we see here is a pretty solid relationship between weight and BMI. And that, in other words, weight, as weight increases, BMI seems to be increasing also, doesn't it? All right. So they tell us in the lab here, they say describe the relationship between them. So we need to go ahead and do that. So down here, I'm going to put in some text down below it, and it appears that as weight increases, so does body mass index, of the BMI. Okay, so that took care of number one. Woohoo! Double space, hit a return. Let's put a space in there to help us out. Okay, now on number two, they want us to work again with the weight and the weight desired. And since, like I said, I'm really not too pleased with the weight desired data set, we're going to skip problems 2, 3, and 4. So we only have to do 5 and 6. So we just need to go down and hit a 5 and a dot because we're not doing number 6 and the rest of those. And they come down here and they say, okay, use numerical summaries and side-by-side comparative box plots to determine if men tend to view their weight differently than women. Okay, so they probably wanted us to use desired weight in here, but we're not going to do that. We're just going to go ahead and compare the weights to each other. Okay, so double space at the end, hit an enter, and then let's go ahead and insert a chunk. Okay, so if I insert a chunk, we're going to come down here, and well, let's see, how am I going to get a box plot of those two variables in there? Okay, well, let's try it. Let's see. How did we do it a minute ago? We went box plot and we said, I want to see what? I want to see if weight is conditioned by gender. In other words, if gender predicts my box plots, right? So it would be a box plot of the weight, CDC weight, right? And then what would I have to do? Well, I got to make this into a model formula. What's the predictor going to be? Well, it's going to be CDC gender, isn't it? Hopefully that makes sense to you, that what I'm doing is I'm saying, well, look, what I want to do is make a predictor of that, right? Okay, so let's take a look and see if that works or not. Oops, my bad. Again, I'm still in the console. You'll find I do that all the time. It's not uncommon that you actually think you're in the console and you're not. And there we go. We have side-by-side comparative box plots, and yes, it looks like there definitely is a difference in the weight of men versus women. Okay, so down here we can say the weight of men appears to be larger than women overall. Duh. All right. Okay, cool. So that takes care of number 5. And let's get down now to the one that's a little bit difficult here, number 6. This is the one I really wanted to make sure that I got a chance to do with you. So let's go take a look at number 6. So it says time to be creative, which means as soon as you hear that, you know that means that they're asking you to apply beyond what you've already learned and take it a step further, okay? So they're asking you to find the mean and the standard deviation of the weight and determine what proportion of the weights are within the standard deviation of the mean, okay? All right, well, I would like to change this slightly. I want to make this so that it makes more sense because, again, there's going to be a difference in weights between men and women. We just saw that. That's what the box plots are showing us. So it would make sense to look and find out if there's a, what the interval of the weights and of within one standard deviation of, say, women or men. And so we'll just pick one of them and we'll go with men. Excuse me, females, not men. We're going to go with women. So find the mean and the standard deviation of the weight of women. And then determine what proportion of the weights are within one standard deviation of the mean. Okay, so let's get going on this. So we're going to have to do a couple of things here. Let's get a new R chunk installed here for us first. So we're going to need to go and parse out just the weights of the women, okay? So we're going to do this in 2 steps. First thing that we're going to go ahead and do here is go and get the F data, which I'm going to call the female data. You can call it whatever you want, but I'm calling it the female data, okay? And so I know that that's a subset, isn't it? I want to get the subset of just the data that are female. And so I'm going to go into my data set, the CDC, and I want to go in and I want to get what? Well, I want it so that gender, CDC gender, is equal to F, unlike M that we had just a few minutes ago, right? And so let's go ahead and run this chunk. And notice now I have a new data frame up here called F data, okay? And so we see this is, you know, what, 10,430 observations and 9 variables, so that's just the women. Okay, so now I have a new data frame that is made up of just the women. I'm going to come back down to the console for a minute so I can take a look at this, and let's type in head F data. Just like a while ago we had the men data, now we got the female data, okay? And just like with the men data, we notice that now all the genders are female. In other words, we parse it out so that in this data set we have all 9 of the variables, but this is only the women being represented in here, okay? All right, so now we need to go calculate a few numbers. They want us to find the mean and the standard deviation of these data. So as we'll see in future work, the sample mean is referred to as X bar. So I'm going to call X bar equal to the mean of, now the data frame that I'm working with is F data. It's not CDC anymore. And what? I want the mean weight among the women. So what's going to go into X bar for me now is going to be the mean weight of all of the women in the data set. And then I'm going to call this STD for standard deviation, and that's going to be SD of the F data, not a date, data, of, again, just the weights. All right, so let's go run just that chunk, okay? So let's do that chunk again so we can see what we got here. So run the current chunk. And now if I come down into the console, you notice a couple new variables got made up there. I can get the console to echo those numbers for me by going, tell me what X bar is equal to. And so the mean weight for the women, this was about 151 pounds. And I can ask it to tell me what the standard deviation was. It was about 34.3 pounds, right? So 151.6 pounds was the mean, and roughly 34.3 pounds was the standard deviation. So that means the average distance away from the mean was about 34.3 pounds. Now, what do they want from us? Well, they want us to create a subset of this data set, F data, and they want it to be within one standard deviation either side of the mean. So how are we going to go about doing that? Well, we need to make a subset, right? But what do we make a subset of? Well, we need to make a subset of the female data. So let's go in and let's make a new data set, and we will call that 1SD. So one standard deviation is going to be equal to what? Well, it's the subset of, we'll see, now where are we going to go get the data from? Well, it's going to be from the F data, isn't it? From the female data, comma, remember this is just like set builder notation, right? And now we got to give the conditions. Well, it's going to be with an and here. Well, what do we want? We want the F data so that the F data's weight is greater than the X bar minus the standard deviation, but less than the X bar plus the standard deviation. That's what we mean to be within one standard deviation. So let's take a second here and do what I just said on the whiteboard before I finish up writing this command. So let's switch over to the whiteboard for just a second. So go back over here to the whiteboard, and let's go ahead and clean this one, get a clean, fresh whiteboard. And so let's see, what did I just say? Well, what we said is that we want to know what is the proportion of the data that falls within the interval between X bar minus one standard deviation and X bar plus one standard deviation. In other words, we want to know how many numbers fall in this interval from here to here, okay? So what we need to do is take and come up with two numbers on the number line. So if this number line right here represented all of the female weights, so this is the female weight here, okay? If this represents all of those female weights in here, there's going to be a mean right here. That's going to be the number X bar. It's going to be the middle of the distribution. This is the mean right here. And what I'm going to do is I'm going to come off this way, and I'm going to use as my measuring stick a standard deviation. And so this point right here is going to be X bar plus a standard deviation. And then I'm going to move down this way, and this number down here is going to be X bar minus a standard deviation. And so what I need to do is I need to come into this data set, and I need to count how many data points fall inside of that interval. And once I counted how many are in there, then I'm going to be able to take that number, divide it by whatever the total number is of the female data set, and I'll be able to tell you the proportion of individuals that fell within this interval from here to here. In other words, what percentage of the females fall within that interval. Okay, so how do I actually do that? What is the command that I need to do that? Well, what do I want? Well, I want them to be larger than one standard deviation, but I also want them to be less, I want to be larger than X bar minus one standard deviation, but I want them to be less than X bar plus one standard deviation. So what that tells me back here in our land now, let's go back over here and actually type this in, is that I need the females, or the F data, weight to be greater than, we'll do the lower end first, to be greater than what? X bar minus 1 STD, right? Because that's we used STD for the standard deviation. And then I need an and in here. An and is how I get an interval, right? So to get an interval, I got to put in an and. To get an and, I get an interval. However we got to look at it. And so then we're going to basically do this command again. We're going to do F data, and then the weight. And this time, what do I want it to be? Well, I want those folks to be less than X bar plus the standard deviation. Okay, so that data set, let's go ahead and run that, make sure that worked. That data set gives me all of the females that are in there. Let's go down and take a look and see if that actually worked. Cool, looks like it did. Notice that it looks like there are, of all of the female data, right, there were 10,431 observations. Of those 10,431 observations, it looks like there are 7,820 of those observations are within the interval. Okay, so we're going to go ahead and just use that to help us out here. We'll come down here and we're just going to go ahead and put in, based upon what we read there on the output. We'll come down here and we'll say it looks like, well, actually, I'm sorry, I want to do this first. Let's go ahead and put it, you know what, I'm going to do inline. Remember, I showed you how to do inline before. Let's do it that way. It appears that there are, okay, so remember how to do an inline. We put in a tick. Remember, a tick is over there above your tab. Then we put an R. Now that's inline code. So I can actually do arithmetic inside of here. It's kind of cool, right? And so how would you do a proportion? So it's going to be 7820 divided by what? Well, how many females? Don't use 20,000 because that would be wrong, because you want to use just the females, which would be what? 10,431 times 100. So we can make it into a percent. Close the tick and then put a percent symbol on there. And then we'll finish off explaining it. Within 1 SD of the mean. Hoo-yah! That was a lot, okay? Let's go ahead and save this bad boy. And let's go ahead and knit it. See what it looks like, see if we get any errors in the knitting here. Ooh, look at that. See, it put our scatter plot right in our document, put our words in there, put our side by side by comparative box plots. And it looks like, what, about 75% are within one standard deviation of the mean. You see, this is the beauty of using our markdown, is we're able to put in the graphs and the text and everything into one document, okay, which is pretty sweet, okay? All right, so let's go ahead and close this, and then we're going to finish one last thing. We're finally done with this. I know it's going to be a little long of a video here, and that is going to cursor down a little bit, put in 4 more hashtags, and we're going to put in text exercises, because what I want you to do is from here down is I want you to put in the textbook stuff, and that's pretty much the way it's going to go throughout the semester, is that the lab will kick off the actual textbook exercises. Now, there was a lot to digest in this lab. I do not expect you to understand everything with just the first pass through it, so be patient with yourself, and this stuff will come. We're going to be doing a lot more work with this, where you're going to get refreshed with all of these concepts that we were going through here, and they're going to start to really sink in and make sense after you've been working with it for a while. Okay, so again, any questions, any concerns, please go ahead and pass those on to me through the discussions forum in Canvas, in particular the one that says questions for instructor, and I'll see you all back here in the next module.